Hi, we are looking at section 6.3 volumes by cylindrical shells. So remember we are still talking about the solid volume of the solid obtained by revolving a given region around y-axis or x-axis or some other line. Now here is an example that we have a piece region. This is our region. So if I revolved it around the y-axis, and notice what shape we get is like a bundt cake. So can we find the volume of this by using the discs? No, because there is a hole in the center. So washers may be helpful, but remember, if you look at the structure of the solid, you might have to do two separate integrals, because this portion below this edge, or this below this circle, is different than the one above the. So probably washer method is not a good idea. So then what do we do? Luckily there is a method called method of cylindrical shells, which makes it easy to solve the problem. And there can be some other cases in which there could be some in which you can solve it both ways, washer or disc or cylindrical shells, but there are some problems which can only be solved by cylindrical shell method. So what do we mean by that? Actually, we start with the same kind of at the same place where we have started other formulas. So we start by partitioning the interval AB. So if we partition that interval AB, let's say we'll partition it like this. So each x sub 1, x sub 2, x sub so on. So let's say there is a kth interval. So there is this interval which is xk minus 1, and the other endpoint is xk. So I will take it separately over here. So think about this kth strip. I'm going to make it a little bit open, or so that we can see clearly what is happening. So this is xk minus 1 and this is xk. So this is our strip. Now if we revolve this strip around this, make it go the whole circle, then you will see that we get a cylindrical shell. That's what we call a cylindrical shell. So this way. So it is get a cylindrical shell. Not a good drawing, but I hope you guys can understand what I'm trying to do. So this shaded strip, it gives us a cylindrical shell. So we kind of like the Riemann sum. So we take the Riemann sum of the volumes of these type of shells. So how do we find the volume of a shell? One of the particular shell, we will say the shell that is produced by this kth strip. So we say by the way, here let me show you how the So this is the region, and the first thing we do is partition it, then pick a strip here and then create a shell. So each piece, each strip will create a cylindrical shell. So creating a half shell from each piece. Now drawing the shells. So this is how and now when you have a lot of those strips, then this is how we get our solid. Okay, so how do we find the volume of a typical shell? So we say let outer radius equal to R2, inner radius equal to R1, and let's say for now height is equal to H. Then remember the area of cross section will be so what will be the cross section if we have a shell? So remember we have in the center it is there is a hole. So we have area of cross section will be the area of the outer circle minus area of the inner circle. So R2 square, pi R2 square minus pi R1 square. I can pull out the pi and I am left with the R2 square minus R1 square. So now the volume, let's denote it by Vk because, well, in here let's just say volume. Of the shell be equal to pi into R2 plus R1 times R2 minus R1 times H. That will be the volume, and now we do a little bit of manipulation here. So it is 2 pi. So I am multiplying by 2 and I will divide by 2 and I will divide this term by 2. And then I have R2 minus R1 and H. So let's see what are these things. So what is this? This is just 2 pi. What is the, how will you call this? This is the average radius, so it is kind of a radius. This is the thickness. And this is the height. Okay, so this is for a, I showed you for a general case. What happens when we have our case up there I showed you where we have our strip is so then in that case, in our functions case, for example, inside this, if you have a create a so what will be the height? Height will be the function f of x. So the radius, remember we are saying, so in our case, the outer shell had the radius xk and the inner shell had the radius xk minus 1. So if you plug in, so you get v is equal to 2 pi, vk is equal to 2 pi times the midpoint, which we can denote here by xk star. And then we find the height at the xk star, so it will be f of xk star times the thickness. In our case, the thickness is xk minus 1, which is delta x. So this is what we get as a volume of the kth shell. Now, as before, we add up n such shells, and that will give us approximate volume, and as n increases it becomes a better and better approximation. And in the limiting case, v is equal to limit n goes to infinity, k is equal to 1 to n. So now what will happen? This will convert into a formula. What is the formula? That I have written here, down here, but I'll show you first why. So notice here the volume V of the solid obtained by revolving the region bounded by y is equal to f of x, y is equal to 0. What is y is equal to 0? The x-axis. X is equal to a and y is equal to b about the y-axis. So about the y-axis. So we are rotating the region about the y-axis. Then the volume is given by this formula. Notice here, from the limit of the sum, Riemann sum. So this thing becomes that 2 pi remains 2 pi, xk star arbitrary, so it becomes x, f of x dx. Delta x becomes dx. This is our formula for finding the volume. So the important thing to remember here is that when you got your solid by revolving the region about the y-axis or around the y-axis, then you have your integral will be in terms of x, or you will be integrating with respect to x. But if you get your region, your solid by revolving the region about the x-axis, then you will have to integrate in terms of y. This is something missing here. V is equal to integral c to d 2 pi y g of y dy.